Okay, well, good morning. Happy Monday. Thanks for being here. Um, we'll go ahead and take a look. So, wanted to just discuss rejection sampling a little bit more. We introduced this last week on Wednesday, and your next homework assignment will have some rejection sampling going on in it. The big idea here for rejection sampling is that we are trying to we're trying to generate random values from a distribution, right? So the idea of having a probability distribution is one thing. The probability distribution has some kind of PDF, some kind of shape, but we want to be able to generate random values from it. And so, we've been looking at some methods for generating random values. We've had the inverse CDF method, which is a pretty good way to generate random values. And then if it's if it's a distribution where we kind of understand its relationship with other random distributions, we might be able to generate values using convolutions. So if we understand how, like a binomial is just a whole bunch of Bernoulli things, we can just generate a bunch of Bernoullis and add them together. Rejection sampling takes another approach. It's similar to, say, importance sampling in that you use a different distribution to end up getting the kind of your target distribution. Importance sampling is not really a sampling method. It's used to estimate integrals, whereas rejection sampling is a method for producing random samples, and that's what we do. Okay, so we'll use random sampling in situations where it's not a built-in distribution from R, and perhaps finding the inverse CDF is challenging or difficult, or just we can't do it for whatever reason. And so the way rejection sampling works is that we have the target distribution, the desired distribution F, that's the PDF, with CDF big F and inverse CDF, big F inverse. And we're going to say, we're not able to generate values from this target distribution. So we find a candidate distribution, a G of X. G of X is another PDF, and the only requirement is that wherever f of x is non-zero, so that is the support of f, wherever f of x is non-zero, g of x is also non-zero. That's kind of the only requirement. And then we find some kind of constant m, such that m times g of x is greater than f of x for all x values in the support. Okay. Now, so that said, we said the only requirement is that g of x is non-zero wherever f of x is non-zero. There are certainly going to be some distributions that are better than others, because perhaps the m that you have to use could end up being some unreasonably large number. And this m, this constant that we will multiply by g of x so that it is greater than or equal to f of x everywhere, the most efficient value is to find the maximum value of f of x divided by g of x. Okay, and so here you can see that because m times g of x has to be greater than or equal to f of x everywhere, wherever f of x is non-zero, g of x can't be zero, right? G of x also has to be non-zero. Otherwise, you're in a situation where you're doing m times 0, and you're expecting that to be greater than f. So, g can't be 0, and then, but yes, you'll find kind of the spot where f of x divided by g of x, some value, okay, and And the maximum of that will always be something a little bit, maybe a little bit to a lot more than 1, just because we know f of x, the entire integral, is 1, g of x, the entire integral, is also 1. So unless they are identical, if there's a spot where g of x is higher than f of x, then there also has to be a spot where f of x is higher than g of x, just so that the total areas are going to be 1, okay? So this is how it goes. So you first generate a random value from g of x, because that's the distribution that we can generate values from. We calculate kind of this acceptance ratio, which is f of x divided by m times g of x. And this value is always going to be a value between 0 and 1. We generate a random uniform value, a random value between 0 and 1, and that will decide whether or not we accept this x that was proposed. So, in step 1, we generate, or I guess propose an x, and we will either accept or reject that. We will accept it if the random u is less than this ratio that we calculated in number 2. If u is greater than that, we will reject it. And we repeat that. So, if you want to end up with a random sample of, say, 1,000 values, you probably have to generate more than 1,000 values in the first place. So we saw this example on Wednesday, but we will revisit it, and I have a little bit of an animation to kind of go along with it. The target PDF that we are going for is the folded normal distribution. So basically, it's the normal distribution just scaled up to be twice as tall because it's only the positive half. So, we need the total area to be 1. We're only taking the positive half, so we're going to make it twice as tall so that the total area is 1. Our candidate distribution is going to be the exponential distribution, which has this PDF e to the negative x. And we can see that this support is compatible with f because they both have the same support, that x is greater than or equal to 0. And so this is what our PDFs look like. And if I told you that the area under the red curve is equal to 1, it also seems reasonable, at least in this picture, to believe that the area under the orange curve is also 1, right? Because both of these PDFs have the same area, and so we can see, there's spots where the exponential is, has a higher density than the normal, and then there's over here the exponential has a higher density than the normal. So that's what we have. The target distribution is the normal. That's going to be our f of x, and then the proposal distribution, our g of x, is the exponential in orange. And so we're going to find the spot where f of x, the ratio between f of x divided by g of x, is at a maximum. And so just using a little bit of math here, okay, so I just do what is f of x divided by g of x, and using calculus, we're going to try to find where is this thing at a maximum. And so so the maximum of this is at the minimum of this little quadratic polynomial here. And so that's going to happen where x equals 1. So right here, and then and that's going to have a value of around 1.32. And so if we take our g of x in orange and multiply it by 1.32, it's going to be taller than f of x everywhere. And so so here is the algorithm just in code. I take that value m, 1.32. I have a function f, which calculates the normal PDF. It's just the normal density times 2. G is just the exponential density. And so, I'm using R's built-in functions here, but I could have written, negative e to the lambda x, or something like that. Okay, I'm going to generate 100,000 values. So I'm going to propose 100,000 values from the exponential distribution using R exponential. and then I calculate the ratio for each of the x values. So this is going to be different for each of the proposed x values, right? So I've got 100,000 proposed x values, and I'm going to get 100,000 acceptance ratios. And those are all found by doing f divided by m times g of x. So it's going to be different for every x value that is proposed. And then which of these things will I accept? So in this case, I generate a big vector of random uniform values between 0 and 1. All of these all of these acceptance ratios are also between 0 and 1. And we're going to find where the value u is less than r of x. So accepted is also, so all of these are vectors, right? So, so this is going to be a vector of length 100,000. Some of these will be true and some of these will be false. And we are going to subset the proposed values just to the values where accepted is true. So some value less than 100,000 there. Okay, and that's it. So this is, here we're kind of taking advantage of R's vectorized operations, right? So sometimes when students see, the steps here, they think of like a loop, and they'll do like 100,000 iterations. That's going to be much, 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 much slower, okay? So, because you can just generate one and then calculate the ratio, generate one u, and then decide to accept or reject it. But in this case, I've vectorized everything. So we're going to generate 100,000 up here. We're going to calculate 100,000 acceptance ratios. We're going to generate 100,000 random uniforms, and then we're going to calculate all of these accept or reject values, accept as true or false, and then we subset based on that. And so this is what it looks like. These are the exponential values, random exponential values that we've generated, okay? And kind of the intuition here is that the exponential distribution, when compared to the folded normal, generates too many values near 0, not enough values around 1, and too many values around 3. Okay, so too much here, not enough here, too many here. Okay, and so so to kind of do this is we want to throw away some of our values in order to kind of get everything to fit. So we're going to scale up basically the orange curve so that the red curve fits entirely under the orange curve, okay? Or in this case, I guess I'll scale down the orange curve to fit, the red curve to fit under the orange curve, okay? And so so this is kind of what it looks like. So I've got I guess our orange curve I've now represented in this blue curve. It's now entirely taller than the red curve. So remember, our red curve is our target distribution. This is what we want. And so if I look at values, say going from say 0 to 0.5, this is the exponential distribution proposes this many values. And we really only want to keep some of them. So basically, we take the ratio between this blue line and the red line, and we're going to throw away a bunch of those. Okay, and so so looking at kind of this span going from 0 to 0.1, if I kind of take the midpoint of that at say 0.05, the density of the folded normal, this height is around 0.8, 0.79689. If you take the density of the exponential distribution after multiplied by m, which is up here, that value is 1.255, and the acceptance ratio is around 0.6347. And so we're saying anytime you get a value between say 0 to 0.1, we really only want to accept around 60% of these things, 63% of them. So, you propose this thing and you kind of have to, you reject it every now and then. Okay. I guess it's I don't know if you have a friend and sometimes you have to try to decide like where you're going to eat if you're going to eat together with your friend, and your friend might have like their favorite restaurant that they every time you say, hey, where do you want to eat, they always say, hey, let's go to Taco Bell or something, and you're just like, I like Taco Bell enough, but I don't want to eat every single meal there, right? So just to kind of like keep your friend happy, but also just so you yourself don't go crazy, maybe you'll like anytime they propose Taco Bell, you're going to be like, maybe you flip a coin and you accept it only about half the time that they propose it, okay? Whereas, so that's kind of over here. The exponential distribution keeps proposing values over here, and the folded normal distribution says, like, sure, I like it. I like values near zero a lot, okay? That's also the highest point in my distribution, but I don't love it as much as you do, okay? And so, you keep proposing this value way too much. So I'm only going to accept, like, you propose these things, I'm only going to accept some of them, right? Whereas, values over here, they don't get proposed as often, okay? And in the original thing, the exponential distribution proposes them a lot less. The folded normal distribution, likes these more. And so whenever a value around here gets suggested, it's going to get accepted every single time, okay? So yeah, the random exponential produces values between 0 and 0.1 too frequently compared to the normal distribution, okay? So if our exponential does propose a value, say 0.05, we're only going to accept around 63.5% of them. So how do we do that? We do that using random uniform. Random uniform will be less than 63.5% of the time, right? So that's how we kind of ensure that only that 0.05 gets accepted with a probability of 0.635. We just take a random U and just ask, hey, is it less than 0.635? And it's going to be less than 0.635 with that probability. That's one of the nice things about the random uniform. All right, let me give you your first view quiz answer. First view quiz answer is the letter B, B as in bear. So that's what we have, okay. Here is just a slightly different value. So we're looking at this bar, 1.4 to 1.5. Okay, so if we're going to take we'll use 1.45 as kind of its center. And so here, the exponential distribution proposes values out here much less frequently than 0. Okay, so this gets proposed, I don't know, with a height of about 1/3 as often here, and the normal distribution out here is also, right around the same height, okay? So if it's not, if their favorite restaurant's Taco Bell and they propose it like almost every single time, but, every now and then your friend proposes another distribution, not as frequently, I don't know, some other place, Chipotle or whatever, and you like it just about as much as they like it, and so whenever it gets proposed, you go, oh yeah, let's go there. Okay, so this is so values around here, will get accepted with kind of a 90% probability over here. So they get so they don't get proposed as frequently, but when they do get proposed, they get there's a higher probability of it being accepted. Okay, and this is just kind of, again, found by doing F divided by M times G for that particular value. And so we're saying values around 1.45 get accepted with a probability of around 90%. And we just kind of, again, generate a random U and accept accept it whenever u is less than 0.9. Okay, and so here is kind of, I don't know if you guys can see this, just a bunch of dots to kind of represent. So all of the dots here are, there's approximately an even density of dots, okay, underneath here, under the blue curve. And that is to kind of illustrate that, yes, values near 0 get proposed more frequently than values out here, just because the density of dots is approximately uniform throughout the whole thing. And so just because the blue curve is a lot lower here, values out here get proposed much more infrequently. So it looks like it did propose a value near 5.0 one time, or 4.0 one time, or so on and so forth. Okay, but we can also see compared to the normal distribution, these values out here, the normal distribution almost, like, very, very, very rarely ever produces a value greater than 3, the normal distribution, or the folded normal. And so the exponential, doesn't frequently produce values around 4, but it proposed values around 4 maybe 1, 2, 3, 4 times, okay? But every single time it proposed a value around 4, it got rejected, okay? It rarely proposes a value around 5, but when it did, that value also got rejected, just because the normal distribution almost never produces a value. Whereas values around 3, it proposed a few of them, and maybe only like one value around 3 got accepted. And so that's this little, represented by, there's a little black dot. Black dots are values that were accepted. Red dots were values that were proposed but rejected. And so this black dot around 3 is a value that the exponential distribution proposed and the normal distribution accepted. Okay, out here, these are all values near 0 that the exponential distribution proposed, and around 63% of them got accepted, and then the remaining 37% were rejected, and that's kind of what we're seeing in this diagram. And so here I said, okay, let's just kind of test it out. Let's just see what is our acceptance ratio. And so these are my empirical estimates of how many values were proposed. So I said, okay, how many values less than 0.1 were proposed out of 100,000, and around about 9,600 values were proposed under 0.1, and we accepted around 6,000 of them. And so that is an approximate acceptance ratio of around 0.6255, whereas our theoretic was 63.5%. Values say around between 1.4 and 1.5. Okay, it proposed around 2,328 of them, and we accepted 2,107 of those. And so our acceptance to proposed ratio there is around 0.905. And our overall acceptance ratio is around 0.755. So our empirical estimates match kind of our theoretic values using the densities of our target distribution and our proposal distribution. Okay. Here, before we get into the more mathematically rigorous proof, I want to show you, I ran this animation thing, and let me see if I can get it to work. Okay, so what we will see here is the this is the red line is our target distribution. The blue line is our proposal distributions multiplied by m, so that we can see it fits entirely underneath the other thing. And the black line is the value that gets proposed. And so so what we will see, it's a little bit difficult to, I guess, keep track of this, but you kind of have to keep track of this in your head. What you're going to see is that values near 0, you're going to see more vertical lines near 0 because these values will get proposed more frequently, and values out, say, above 3 or 4 will get proposed much less frequently. So here we're proposing a value of around, I don't know, 0.9 or 0.8, okay? And then, and here we're going to generate a random U, okay? The random U is going to go from 0 to 1. So whatever the height of this black line is, the top of the black line is 1. And so in our case, we are, I don't know, about 40% of the way up, 38% of the way up from the bottom to the top of the black line. So this random U is underneath the red line, so it will get accepted. Okay, so that one's going to be accepted, and we will I will put a dot here. Okay, over here I'm proposing a value close to 0, maybe around 0.1 or something. And again, that's because the exponential distribution proposes values near 0 very frequently. I'm going to sample a random U. Again, the bottom of the black line is 0, the top of the black line is 1. Okay, so again, as we move up and down the x-axis, the kind of where 100% the maximum, this is like your the top of the scale is at 100% wherever it is. And so in this case, the U that we proposed is, I don't know, 0.98 or something close to the top. So just ignore the density. That's unrelated to where U is going to be. It's, you know, between 0 and the very top being 1, so it looks like 0.95 or something. And so that is above the red line, so that's going to get rejected. Here is another random value. The top of the black line is going to be 1. Let's see. We generate a value of like 0.98 or something, so that's going to get rejected. And so as I'm going on, values that get rejected, we're going to kind of keep where it is in red here, and then, you know, values that do get accepted will show up in black. So let me, here, I'm going to zoom in a little bit, and I'm going to just let the animation run. And so it's operating very quickly. It's just, again, generating random values. And you see the vertical lines mean that values near 0 get proposed more often. If you don't see a line, it means it proposed a value kind of like way out here. So, you know, we're seeing values closer between 0 and 1 get proposed more frequently. Every now and then the line will appear out here. And we sample, you know, wherever the line appears, we sample a random U. And it's just kind of going through. Anytime the U ends up above the red line, it gets rejected. So a lot of these things do get accepted, but every now and then, yeah, that, you know, value gets rejected. And you'll notice, yep, a value out here got proposed and it got rejected almost. That got rejected right away. So, and so we can see, as far as the values that do get accepted, they're going to follow the density of the target distribution in red, and not and values out here all get rejected, and some of the values between 0 and 1 get rejected, but, you know, a lot of them do get kept. So this is so you can make little animations in R. You can okay, I guess that was it. All right, and you can slow down the speed if you want or whatever. I can share my code for this. All right, so that's our animation there. Let me I didn't know there was audio coming in through here. Okay, let me just show you another example. This time with the beta distribution. Okay, so let me. Okay, what do I need to do here? I think my x limit, I'm going to go from say -0.1 to 1.1. I hope this will do it. Oh, how do I change my vertical axis? Going from S to G. S will go from 0 to 1. F, G, I'm just trying to keep track of things in my brain here. My M is going to be, my M I want to be 1.5, yeah. Ignoring that plot, let me reset the animation, propose accept. M times G of S, aspect ratio, oh, let's, I don't know what the aspect ratio should be. We'll delete this. Plot S times M times G of X, I think. Oh, okay, I gotta do Y limbs. 0 to say 1.6. That should do it. Okay. All right. Let me reset my animation. Missing U. Missing value where true false is needed. It's our classic error encounter. Proposed X, U, M. Missing. Coding live is always a risky. Now I got to make sure I don't overwrite my old save file. Save as rejection sampler. This will be beta distribution. Okay, let me just. Put in a U for I in 1 to n. Okay, we're going to plot this. We're going to look at that. If I is greater than 1, starting with the second iteration, plot the previous points. U times this, propose an x from, oh, okay, not R exponential. We want to propose a U from R uniform. That's what's going on. Okay. And then the height of the segment is going to be that. X is just 1 proposed. Okay, I think. Oh, this is not a good sign. Oh, okay, it looks right. It looks right. And then we're going to save this as beta rejection sampler. I hope this worked. Okay, oh, great. It looks like it's working. Okay, so here, now I have the beta distribution. We're going to do rejection sampling here. We're going to propose values between 0 and 1 from the uniform. And here we can see the beta distribution has a very different shape from the uniform distribution. So basically so the uniform distribution is going to propose values between 0 and 1 with equal probability. But anytime it proposes a value near 0, we're going to reject every single one of them. Anytime it proposes a value near 1, we're going to reject almost every single one of them. Values near 0.5, we reject 100% of them or almost of them. So, so this value got proposed, and so it really all depends on what our U is. And so in our case, 0 is at the bottom, 1 is at the top. And so, so in this one, looks like we're proposing, I don't know, 30% or something. So we will we'll accept that. This value almost, unless it generates like a U that's 0.99, we will accept it. And it generated 0.95, so we're okay. We accept it. We'll see what gets proposed here. So here we're proposing also kind of a 0.95, but in this case, the value we proposed was 0.2, and so that one's going to get rejected. Okay, and so again, the animation, you're going to see the black line appear with equal probability along the x-axis, and just sometimes it gets accepted, sometimes it gets rejected, as long as it's under the red curve. So this one barely made it under, and this one barely got rejected, but it got rejected, right? And so, so here we're just proposing a whole bunch of values between 0 and 1. We only want to accept some of these depending on what value it is that we're proposing, and we look at kind of the ratio between our target PDF and the proposal PDF. And in our case, the proposal PDF is very simple, but this will give us a kind of a sense of how kind of the rejection sampler is working. Okay, and I guess I'll share my little scripts here so you can install the animation package in on your computer. And I don't know, I enjoy doing stupid stuff like this for fun. I don't know what your hobbies are, but making little animations for teaching stats, that's my kind of thing. All right, let's see. Okay, but anyway, that is the rejection sampler. Rejection sampling. Okay. All right. So now we'll spend a few minutes. Oh, let's see. Second view quiz answer. Second view quiz answer is E. E as in elephant. E is our second view quiz answer. Okay, and then we'll spend just a little bit more time going over, I guess, more mathematically rigorous proof. And again, my disclaimer is that I always struggled with proofs in my academics. I was always more comfortable writing code and stuff. But here we will. What we want to show is that even though we use the function g of x to propose the random values of x, is that if we only accept some of them with this probability R of x, then the resulting distribution is going to be equivalent to the f of x, right? So we want to show that the probability that x takes on any particular value is going to be equal to the target PDF, because that's what we want to show, as long as we condition the x values on this kind of acceptance rule. Okay, so using this, what we're going to do is we're going to use Bayes' rule here, and so we're going to say, the probability that x gets accepted, the probability of any particular value of x appearing in our distribution, given that it was accepted, can be found using Bayes' rule by saying, hey, what's the probability that it was accepted, given that we kind of proposed multiplied by the probability that we even proposed it in the first place, divided by the kind of, what's the probability that x gets accepted anywhere here, okay? So, the probability that x is accepted for whatever particular value of x is we're going to use the acceptance ratio, okay? This is our rule for whether x gets accepted. And so we're going to take a random uniform value, and we're going to ask, is the random uniform value less than this acceptance ratio R of x, okay? What is the probability that we even generate x in the first place? The probability that we generate x in the first place is g of x, because that is the PDF or the distribution that we're using to propose our values. And then what is the probability that just x gets accepted regardless of what value x is? This is just going to be the entire integral of this entire thing here, okay? So, and we know that the denominator is just the integral or the sum of the numerator across all possible values of x. It's just here we have infinitely many values of x. Okay, so what is the probability that u is less than our acceptance ratio? Well, that is just our acceptance ratio itself, okay? The probability that u is less than this is just going to be our acceptance ratio. As long as our acceptance ratio is between 0 and 1, and that is the case because we put in this rule that m times g of x is greater than or equal to f of x everywhere. This is working under the assumption that m was selected with that criteria in mind. And so the acceptance ratio is going to be f of x divided by m times g of x. That is that. And so, these g of x's will cancel, and in the numerator we'll get f of x over m. This over here, the g of x down here also gets integrates out, or cancels out, and so we have the integral of f of x divided by m. The integral of f of x across all possible values of x is going to equal 1, okay? And that is, I guess the other condition for this statement to be true is that, the support of f of x is contained entirely within the support of g of x. So this curly brace x represents the support of g of x, and even if there are values in this x that are not part of the support of f of x, those are all just 0. So anyway, the integral of f of x across all possible values of x is going to equal 1, and so we have that, and so this all just cancels out. We have f of x over m divided by 1 over m. The m's cancel out, and so the final probability that we take on a particular value of x follows the PDF of f of x, which is the target distribution, and that is exactly what we wanted to show, and that is what we have here. Okay, we're going to finish early. I guess 8:50. All right. All right, so I do want to throw in this final slide to just kind of make sure that we don't get these two things mixed up. Just because their names are kind of similar, and what you do are also kind of similar, but they serve entirely different purposes. In both of these cases, we have the problem of not being able to generate values directly from the target distribution f of x. And both of these methods take the approach of using a different distribution, g of x, and having some kind of ratio. The key difference here is that rejection sampling is a method used to generate values, random values from your target distribution. So if your process requires that you actually have random values that you can then use, you're going to use rejection sampling. And rejection sampling means you're going to propose some values, and some of those values that got proposed get thrown away. Whereas importance sampling is not used to generate the values. You don't actually care about the x values themselves that were generated directly. You are using those x values as a means to estimate basically the integral. So we had Monte Carlo integration, and we're saying, hey, we want to estimate this function, the value of this function here, and we just need to be able to in Monte Carlo integration, the way it works if we are able to generate values is we just generate a whole bunch of values, plug them into the function, and we take the average to get our estimate. And here we're saying we weren't able to generate values from that function directly, so we're going to generate something else. We still want to plug them in and get an estimate, but in order to kind of correct for that, we weight all of the values that we generated. So importance sampling, we don't actually care about the x values that were generated. We just kind of weight them all, and then we take the average to get an estimate. Whereas rejection sampling, we actually do care about the individual values because we want a random sample. So that's what we have. Rejection sampling does throw away some of the values. Importance sampling doesn't throw anything away, but we just weight some of these values less important as others, give them a lower weight. And so, personally, I don't like the name importance sampling just because it sounds like it should be generating a sample, but it's not. Okay, it's used to calculate an estimated of a thing, but that's just the name that's in the literature. They call it importance sampling, even though it's really Monte Carlo integration. And I would say weighted Monte Carlo integration makes more sense, but that's not the name. So don't go around calling it weighted Monte Carlo integration, because that's just my opinion, not the name of the literature. Okay, a little bit. We'll just end a little bit early today, and I'll give you your final view quiz answer. And final view quiz answer today is the letter A. A as in apple. A as in apple. Okay, we'll wrap it up here, and then on Wednesday we'll take a look at generating values from like a multivariate distribution, because sometimes we need to be able to do that as well. Okay, we'll see you on Wednesday.